Neeraj, we can't hear you.
I have not started. Can I start?
Yes.
Okay. Thanks. Good morning, everyone. I am Neeraj Gupta. I am a faculty at IUCAA, as you have been listening to many lectures, and this is now probably coming towards the end of the summer school. And I'm going to give you 3 lectures on radio astronomy, and I would focus more on the techniques of radio astronomy, and also I will highlight some of the discoveries that have been made over the years in radio astronomy. And I will conclude my third lecture with some of the future telescopes that are coming online and that would completely brighten the field of astronomy in general. So in the first lecture today, we would try to get the idea of how radio astronomy started, what radio astronomy is, and we will develop some of the basic tools and the machinery that will allow us to then understand some of the complex concepts involved in radio astronomy. So straight away starting with that, what is radio astronomy? So radio astronomy, when we refer to, we are talking about studying natural radio emission that comes from celestial objects, and these objects be suns, stars, galaxies. They could be gas clouds in our galaxy or in distant galaxy, and even cosmic microwave background radiation. And the radio telescopes that we have today, and there is a huge variety of them, and we will look at them during the course of lecture. They are capable of detecting radio waves from very nearby objects, stars, and even from the earliest stages of universe. And and another special thing about when you look at radio astronomy is that we're talking about astronomy at some of the lowest frequencies of the electromagnetic spectrum. But this should not be confused with that we are trying to observe phenomena at low energies. And you will come across that in radio astronomy, actually we are most of the time studying some of the most energetic processes and objects in the universe. So that's the one slide overview of what radio astronomy is. And as all of us know, that radio waves, like light, are electromagnetic waves. And the theory of their propagation is then based on Maxwell's equations. And that is something I'm sure you have covered in detail in your coursework as well as in first few weeks of the lecture. And what Maxwell's equations are, you're very familiar with. Here they are on your slide, just for a quick recap. And you know that first one is the Gauss's law that tells that net electric field through a closed surface is proportional to the enclosed charge. Then we conclude that there are no magnetic monopoles. And then we have Faraday's law and Ampere-Maxwell law. These partial differential equations essentially relate electric and magnetic fields, currents, and changes of fields. That's what these contain. And a solution of these is a second order differential equation, which I'm sure all of you have also solved. And it describes the propagation of EM waves in vacuum or any medium. So we can solve these Maxwell equations for various media. And when we solve it for vacuum, we get a solution which tells us that electromagnetic waves are nothing but E and B fluctuations, electric and magnetic field fluctuations that are perpendicular to each other. You can follow my cursor here. And they're also perpendicular to the direction of the propagation, right? Now, an EM wave or electromagnetic wave is represented by a complex number. I'm sure you're also familiar with complex algebra. What we are trying to say here is that it is actually two quantities that we are interested in. One is amplitude and another is phase. So we can write the electric field vector like this. The first term is the amplitude here, and then this second term in the exponential represents the phase of the field. And when we measure its brightness or intensity average over time, as represented here, we are actually losing the phase information completely. And this is what happens when we are detecting this signal through our eyes or in photographs, right? But we also know that electromagnetic waves interfere. So if I consider a situation where the same wave is traveling along two different paths, Here, let's consider E1, A1 exponential iota phi, and then this is the second wave. Let's say it is traveling through a different path. So there is a phase difference between E1 and E2. And if I consider the superposition of these through this, then I come across this expression where I don't only have A1 square plus A2 square, but I also have an interference term, which I refer to as the fringe pattern. And if you recall, this term is nothing but the term which comes in your Young's double slit experiment. And this fringe pattern, you will also recall that that we have on the screen is actually very sensitive to our position on the screen. And it's also very sensitive to the slits or the coherent sources that we are using in the experiment to generate this fringe pattern. And this is a very important point, and I would like you to, I'm sure you all of you know about this experiment and have worked out the details of it, but please keep this fresh in your mind, because especially in the second lecture when we talk about interferometry, we will visit this time and again, and familiarity with those concepts would really help you to appreciate how radio telescopes work and how we make images of sky using various radio telescopes. So if there has to be a takeaway from today's lecture, and you want to go back and ask yourself that, okay, what is it that I must revise or refresh for subsequent lectures, then it would be this fact that electromagnetic waves interfere, and this interference pattern contains information about the spatial structure from where the radiation is coming, that is the details of the source, and also the spectral information that if there are some spectral lines, that is also contained in it. And in fact, Michelson used this technique to specifically build a stellar interferometer to measure sizes of stars and also to derive spectral information from what we call fine structure of lines, which he later actually used to standardize the meter in terms of red line of cadmium, right? And in 1907, Michelson was actually awarded Nobel for the development of these instruments and investigations he carried out using these instruments. And we'll look at Michelson's experiment in more detail in the next lecture. But let us always remember that electromagnetic waves interfere, right? So now, what is it that we refer to in electromagnetic spectrum when we say radio astronomy? So you can look at this plot here, which is showing the transparency of the atmosphere on y-axis. On x-axis is the wavelength, right? So what this is actually showing that, or telling you that the radiation from the sky, which can actually pass through our atmosphere, and we can do, for example, ground-based astronomy in this wavelength regime, and there are some small windows here. But otherwise, there's a lot of region here which is completely opaque. So if you want to do astronomy, for example, here in ultraviolet or in X-rays, then we need to set up telescopes in space. And we know that we have Hubble Space Telescope and Chandra Observatory and many other instruments that are set up in space to observe galaxies and other objects at these wavelengths. When we talk about radio window, we are referring to this range which goes from approximately 0.3 millimeter to 30 meter. So it covers actually 5 decades in frequency, right? And that's what we will refer to as radio window here. One special thing about radio astronomy is that it is also extensively used by us for many other purposes. For example, we have microwave ovens, mobile phones, our Wi-Fi devices, or the signal itself, then FM radio, television. All these things emit radio waves in the radio window. And as we will appreciate later, that the signal that we are anticipating from celestial objects is much, much fainter than these. So you would notice that almost all the radio telescopes that we have, or especially that are being planned for future, are built in what is called radio quiet zones. What we mean by radio quiet zones is that we either go to a place where there is very less civilization, so very few people living there. So go to very remote places so that there are no people not using these devices, or we If you can't do that, then we put some restrictions around the area where we have a telescope. For example, we don't allow people to come with their mobile phones and switch on them. We don't allow microwave ovens. So, for example, if you go to Giant Meter Wave Radio Telescope, which is one of the largest telescopes in India, you would find that as you approach it within about 2 or 3 kilometers, you start seeing various notices telling you to switch off your mobile phones. And as you go inside it, you will find that it's a totally different world where you will not see any microwave ovens or any other electronic devices which can actually radiate and interfere with the signal that is coming from the space. Okay. So what is it that, so let us try to understand now what is the lower bound and the upper bound is coming from in radio window. So lower bound is coming from the molecular absorption in the atmosphere. And what happens that in the atmosphere, there are several molecules which very strongly absorb radiation here. So it becomes completely opaque. And if you want to observe at some of these frequencies very close to, let's say, 1 terahertz here or the millimeter here, then we have to go to very high altitude sites such as in Chile, where Atacama Large Millimeter Array is there. And there we can still observe frequencies close to a terahertz or something like 3 millimeter we are referring to in wavelength. The higher, longer wavelength or the shorter frequency cutoff is related to another layer in the atmosphere, and that is ionosphere. And what happens, you would know the concept of plasma frequencies. What happens that if you solve Maxwell's equations for plasma, you would come across the concept of plasma frequency, which tells that only those waves that are allowed, that have frequency greater than the plasma frequency, are allowed to pass through the plasma. Otherwise, the refractive index becomes negative and waves cannot propagate through. So the plasma frequency sets the lower cutoff for the frequencies of electromagnetic radiation through the ionosphere. And for ionosphere, if we take the values of electron density and other quantities, then we find that the plasma frequency actually corresponds to approximately 10 megahertz. So the wavelengths longer than 10 megahertz become almost impossible to observe from ground. If one wants to observe them, then one will have to go to space. And there are plans to build even radio telescope in space to cross this barrier. And of course, you know that even though I'm presenting this ionospheric cutoff as an obstacle to radio astronomy, but it has been a very useful thing for us when we talk about telecommunication. The fact that radiation of certain frequencies get reflected back is widely used in telecommunication, and you are very much familiar with it too. So now let's see where does radio astronomy sit physically when we here in the previous slide we were talking about like where it sits in when we talk about the wavelength range, but here let's try to look at the images of our galaxy at different wavelengths. And starting at the top we have radio continuum, and then we have second panel is showing the image of galaxy in neutral hydrogen. This is the line at 21 centimeter wavelength. And then again radio continuum, but it is now at higher frequency. You can see it is 2.5 gigahertz. The first panel was at 408 megahertz, and you can see that in all four, even though they are radio, it is looking different, right? And why is this happening? Because we are actually looking at different physical processes that are taking place in the interstellar medium of our galaxy. As we go to really long wavelengths, we are looking at supernova, or the emission that is coming from synchrotron radiation, which is nothing but cosmic rays or relativistic electrons going around the magnetic fields in the galaxy. And as we are coming to higher frequencies, we are looking at free emission that is coming from H2 regions. And of course, then we have this neutral hydrogen line in the second panel, which is showing us how the neutral hydrogen is distributed in the galaxy. And you can see that most of it is actually confined to the plane of the galaxy. right? And when we go through other panels, you will find that it begins to look even more different. Infrared, we are looking at older stars. If we come to optical, we are supposed to see a lot of stars, but we not just that, we also seeing lots of dust obscuration here, right? And when we go to even higher frequencies, we are looking at starting to look at some of the other more compact energetic objects in the galactic plane that we have. So one thing that is very straightforward to conclude here is that radio waves are longer. They are longer than dust grains that are present in the interstellar medium, so they are unaffected, which means that radio astronomy provides us a dust unbiased view of the universe. So in this sense, it occupies a very unique place in the astronomy. That if you want to look at places which are obscured in dust, then radio astronomy or the radio wavelengths are the wavelengths to choose for. Okay. So now let's try to understand how it all started, because it will also give us an idea of how uh, the technology evolved initially, how it made it difficult for radio astronomy to take off, and that takeoff was not smooth, as you will see. And then as it evolved, how it led to some of the major breakthroughs in the field of astronomy. That's the idea of next few slides. So now going back, you would recall that radio waves are nothing but electromagnetic waves, and they have been known for quite some time. Actually, you can go back to 1887 when Hertz actually demonstrated the existence of radio waves, and in the same century, radio waves were also discovered. Or sorry, electromagnetic waves were also discovered at infrared and near UV, and in fact, they were discovered almost 70 to 80 years before the uh, Hertz experiment took place. And as soon as these waves, radio waves, were discovered and existence was known, people actually started thinking from that moment itself that can we use or observe celestial objects at radio waves? Can we, for example, observe sun and look at its radiation to see how it looks at radio wavelengths? And some attempts actually started to take place even at that time. But you But the astronomy at in those days, or our physical understanding of celestial objects, was very much based on how our understanding of physical processes in those objects, and that was mainly dominated by what is called thermal processes. What we're talking about here by thermal process is that an object is emitting radiation because it has got a certain temperature, and you know that in such a situation the brightness of the source is can be described by this Planck function, which goes as 2h nu cube by c square, and here exponential h nu by kt minus 1. And while we are at it, I should quickly describe that in at very long wavelengths, especially in the radio wavelength regime, we can use this Rayleigh-Jeans approximation. And in this approximation, it can actually be reduced to this much simpler expression. And if you take sun, for example, our sun, for example, and ask the question that what would be its flux density if I place it at 1 parsec, you would find that its flux density is actually 0.3 micro Jansky. So micro, of course, you know, is micro is 10 to the power minus 6. And what is Jansky? Jansky is actually 10 to the power minus 26 watts per meter square per hertz, right? That's such a weak signal that we are anticipating from even sun, which is so bright and close to us as we know, right? And why I chose 1 parsec, because this also distance to the nearest star that we have, that is 1.3 parsec. And if I want to detect an object of this flux density, even with, and I take the most sensitive radio telescope that we have, it would take like tens to hundreds of hours of observing time. So you can see that it is really difficult to, even though an object may look very bright at optical wavelengths, it depends on what physical process through which it is illuminating, that it will determine whether we can see it at radio wavelength or any other wavelength or not. So that was one of the main reasons that initially people were not only skeptical that they would detect any objects at low wavelengths or long wavelengths, because it was anticipated that the flux density is going to be very, very small. And another aspect, at that time, ionosphere was not very understood. So because in today's lecture, we just covered that in our second or third slide, that wavelengths longer than 10 megahertz wouldn't pass through the ionosphere. But in those days, electron density and those properties were not determined. So people did not know that at what frequency to set up the experiment. So these are two very important aspects of setting up any experiment, in particular an observation here of a celestial object, that we need to understand at what frequency or wavelength to observe it, and for how long to observe with an instrument. Because if we optimize these two aspects, then only we can carry out an experiment which is reasonable. Otherwise, it can lead to a failure, which was happening initially because some of the earlier attempts were to observe sun and other objects at very long wavelengths. Because if you look at here, the flux density is going to be very, very small there. So it was both lack of the physical understanding at that time as well as the technology that led to slow start of radio astronomy. But finally, when we come to 20s and 30s, the radio astronomy finally took off, and that was a serendipitous uh, takeoff actually. And the person who is responsible for this is Carl Jansky, and that's why, in honor of Jansky, the unit that we use in radio astronomy to measure flux density is called Jansky. And he was an engineer at Bell Labs, and he was actually trying to uh, investigate a particular noise that was appearing in the transatlantic communication signal. And that noise was annoying, and it was leading to loss of revenue for the Bell Labs. So idea was to investigate what is causing this noise, address it, and then make the communication really comfortable. So he set up this antenna, which you can see here, and his experiment was actually at 20.5 megahertz. So you can see that it's so close to the ionospheric cutoff that we have here at the 10 megahertz. And he started investigating what are the possible sources of noise in the signal. And he started locating most of them to various thunderstorms which were taking place in the region. But there was a faint noise which was always present in his signal, and it always increased at a particular time and it fell subsequently, and it repeated every day. Initially, he thought that this may be coming from sun, but as he did more and more observations, he found that the, re, the recurrence of this noise is actually repeated not after every 24 hours, but it is 23 hours and 56 minutes. And this is, as you would know from basic astronomy, is the characteristic of fixed stars, the motion of fixed stars in the sky. So from this, he was able to conclude that it's not something which is terrestrial or local. It's actually astronomical in nature. And with more effort, he was actually able to pinpoint that this is actually the direction of the center of our Milky Way galaxy, and actually coming from the constellation of uh, Sagittarius. So this was the first detection of radio wave from an astronomical source. And you can see here in the chart recorder this periodicity that is of the signal that is appearing here, right? So he single-handedly, but it's not that as soon as the discovery happened, people started doing radio astronomy, because Bell Labs was a commercial setup, and of course they were doing a lot of engineering discoveries at that time in the field of communication and signal processing, but they were not really interested in astronomy. So as soon as they solved their problem, they moved on with their other activities and not really pursued it. So it actually required an amateur astronomer at that time, and we would call him the first professional radio astronomer, because he not only made a lot of discoveries but also published them in journals as professional astronomers do nowadays. So he single-handedly built a 10-meter parabolic reflector in his backyard, and this is world's first astronomical radio telescope, you can call, built specifically for the purpose of radio astronomy. And then he thought, like since he knew that Jansky observed at very long wavelengths and discovered signal from the galactic center, he thought if I do my astronomy or observations at much shorter wavelength, that would be perfect. Because if I go back to this plot, you would see that any signal if I take and if I go to higher frequencies, here you can look at this expression also, the signal gets stronger. So this is the anticipation that is coming from the thermal nature of the emission. But he detected nothing at 3300 megahertz. But he did not give up. So he moved to 900 megahertz and detected nothing. And then eventually he moved to 160 megahertz in 1938. And then he confirmed Jansky's discovery with higher spatial resolution because his antenna was bigger. And we will see why a bigger antenna would give you higher spatial resolution later in the lectures. And he also published his results in in a journal. And he carried out these observations at multiple frequencies. So he was also able to characterize the slope of the brightness of the radio sources. In his observations, he detected Milky Way, Sun, Cassiopeia. These are some of the brightest objects in the sky. And his observations were at 160 and 480 megahertz. And he published results in FJ. That's why I called him like first professional radio astronomer. So what he found or discovered observationally that radio emission is non-thermal, which means that in the kind of objects he was observing, he found that their brightness actually was increasing as you go towards lower frequencies. And around the same time, physicists such as Ginsburg came up with a theory that this emission is actually not due to thermal processes like the black body or as characterized by Planck spectrum. They're actually coming from motion of relativistic electrons in the magnetic field in the galaxy or in other objects. And the name for such process is synchrotron emission. So these early observations led to the observational discovery of a new physical process and also the development of the theory to explain it as well. Once that happened, then radio astronomy took off in a big way because the economic circumstances also were favorable to it. And another 10 to 20 years within that much time, there were lots of objects that were radio objects that were detected in the sky. And situation came that like people detected these objects, but they didn't know what they are. So what people started doing was to look at them in optical wavelengths and try to see what they could be. And try, because optical imaging can show different aspects of the object, but you can also take what is called as a spectrum of the object at optical wavelength. And then from that, you can start inferring physical conditions in the gas and in that object. So what they found, for example, for this object, which was called 3C273, it corresponds to a very bright radio source in the sky, that it showed a certain spectral lines, which, and these spectral lines were actually nothing but redshifted by a certain amount. And in this case, redshift of 0.370. So this established straight away that this enormous radio emission is actually coming from not a local source, but a distant source. And the amount of energy, because since we know the distance, we can now calculate the luminosity of it, is enormous. And such objects are called quasars or active galactic nuclei. And in these objects, there is an accretion disk, and matter from that accretion disk is actually, when it falls towards the black hole, enormous amount of energy is released in the form of electromagnetic radiation. So some of the first quasars like 3C48 and 3C273 were discovered in late 50s. And first they were found as radio sources, but then with the optical identification, we knew that they are distant sources, they are AGNs. And now actually this is a completely well-developed field on its own. There are more than 600,000 quasars known at present. A large number of them have actually been discovered using what we call slow and digital sky survey. And observations of these objects, like of course AGNs themselves are very interesting, but they are also excellent probes of studying all the intervening matter that is there between quasars and us. So they have also allowed us to study objects like galaxies, which are very far away, very faint, we cannot detect them directly, or they have allowed us to look at very faint matter an intergalactic medium, for example, which is so faint that we will, or so diffuse that we cannot detect directly in emission. So quasars have also been used as excellent tools to study distant universe, black hole formation, and properties of all the intervening matter. Next, in, for, in 40s, you must be familiar with 21 centimeter line of hydrogen, which actually comes from interaction of electron and protons moment. So what happens that when electron and proton spins are parallel, it has one energy state, and when they are anti-parallel, it has a lower energy state. And in a magnetic field, there's a slight difference between the energy of these ground states, depending on whether these spins of the proton and electron are in the same or opposing sense, right? And the transition between them gives rise to a line close to 1420 megahertz, with like 21 centimeter in wavelength. This is why this line is called 21 centimeter line, and is a most powerful tool for studying the dynamics of galaxies and also neutral hydrogen in general in the universe, because as you know, neutral hydrogen is the most abundant element, and also like it's a building block for almost everything that we see in the universe. So this line was predicted by van der Hulst in 1944, and as soon as it was predicted, astronomers started developing setting up observations, and in 51 it was finally detected by three groups almost simultaneously: Ivan and Purcell in USA, and then Oort and Muller in Netherlands, and Christensen and Hinman in Australia. And since then it has emerged as a very powerful probe of galaxy evolution, which is to understand like how galaxies formed and evolved. Then the discovery of cosmic microwave background radiation. This was another major discovery that happened at radio wavelengths. This was again serendipitous, very much like Jansky's observation. And this was also done while characterizing noise sources for satellite communication in this case, because now we are talking about 60s and not 30s. And this was awarded Nobel Prize in 1978. And we all know that like CMB has made such a big impact in our understanding of the universe. Then discovery of pulsars. This actually has got two Nobel Prizes. First one was for the discovery itself. It happened in 1967. And initially, when it was discovered, people thought that these pulses, which are coming from highly magnetized rotating neutron stars, are actually perhaps coming from some external civilization. But when few of them were discovered, it was found that okay, that's certainly not the case. They are actually celestial objects. And another Nobel was awarded to the observations of what we call as Hulse and Taylor pulsar. It's a binary system in which a neutron star is actually rotating around the common center mass of its companion, which is a neutron star. And in that case, the Einstein's theory of relativity predicts that with time the system should lose energy, and that should change the pulse period. And that was certainly observed and confirmed observationally, and it provides a very nice test of Einstein's general theory of relativity, and again Nobel awarded in 1993 for that. So these were some of the examples, like although there was a slow start for radio astronomy, but when it took off finally, it has led to a lot of exciting discoveries that have actually developed into field on their own, and it has hugely impacted our understanding of galaxies, AGNs, pulsars, and universe in general. So now we will move into trying to understand how actually radio astronomy functions. How does it work actually? So let us first try to understand how signals at radio waves are detected. Okay. And what I am showing here is a picture of a giant meter radio telescope. You can see there are several dishes. It has multiple dishes. In total, in fact, there are 30 dishes, and each one has a diameter of 45 meters. And these dishes are placed over 25 kilometers. And there's a very specific reason to choose these antennas like this and place them in this manner over a certain distance. Of course, the ultimate goal, as you would know, is that to detect faint objects and to be able to detect details in them. So that must be the motivation of it. But we will try to understand in today's and the next lecture that why one does that. And if you haven't done so, if you get some opportunity in future, you can try to visit this telescope, which is near Pune. It's one of the world's largest radio telescope. And it's very exciting to visit the observatory site. Of course, as I told you before, you will have to switch off your mobile phones as you reach there. So when we talk about detection of radio waves, the most basic or the simplest detector that we are talking about here is the dipole antenna. And in radio astronomy as well as in telecommunications, a dipole antenna is the simplest and most widely used class of antenna. It is also a very simplest type of antenna from a theoretical point of view. You would recall that uh, Hertz, when he first demonstrated the existence of radio waves, he was actually using a dipole. And you can see from this cartoon here that a dipole consists of two conductors of equal length oriented end to end. This is one type of dipole that we have shown here. And there's a feed line which is connected between them. What happens in the dipole antennas like this, the fundamental resonance of a thin linear conductor that is here is actually depending on the frequency whose free space wavelength is twice the wire's length. So what happens if you take a half-wave dipole antenna, which consists of two quarter wavelength conductors, which are placed end to end for a total length of, let's say, approximately lambda by 2, this total being lambda by 2, that's why calling it half-wave dipole. In this case, what happens is the current distribution is that of a standing wave, which is sinusoidal along the length of the dipole, with a node at each end and an antinode at the center, which is the peak of the current, right? So if we look at what would be the power distribution or power response of such a dipole, this is shown here in one dimension here. You can see that the radiation pattern of this half-wave dipole is maximum perpendicular to the conductor. You can see the dipole here also. And it is falls to zero in the axial direction. So what we get as a result of this is an omnidirectional antenna if it is installed vertically. And if you look at it in 3 dimensions, which is shown here, the power pattern actually looks like a donut or a toroid, which is and it's perpendicular when it's perpendicular to the dipole's axis, right? So what we get through this dipole is a omnidirectional antenna, which is when it is installed vertically, and it's very weakly directional if it is horizontal. So you can quickly understand that although it's a very nice simple unit to detect radio signal, but for a telescope it is not a very nice setup. Why is that? Because when we are trying to receive radio signal from the space, we would also like to know that from where the signal is coming. And if my antenna is omnidirectional, which means it has almost same response everywhere, then I cannot tell whether signal is coming from a particular direction here or a particular direction there, and then I may not be able to do much with that signal, even though I may detect with that. So next step is to try to understand what a good antenna would be. So we will try to understand in next few slides that when we're talking about a good antenna for radio astronomy, we are essentially looking at two properties. One is the gain, which is which corresponds to the sensitivity is able to detect faint signals, and second is the directivity, which I was referring to a short while ago, where we want to know if we detect a signal from which direction it is coming from. So let us define some of the basic properties or basic quantities through which we can identify a good or a bad antenna. So what is shown here on the right, if you look at this figure, a typical power pattern of an antenna, right? So it has a main lobe, the central one where the response is maximum. But an antenna will also have what we call a side lobe. So there are these smaller lobes where the response is not going to zero. And then it can also have a very small back lobe as well. And these properties may be better or worse depending on what kind of antenna that we are talking about. So first thing that we define what is called the beam solid angle, which is called as omega A, and P is nothing but the power pattern which is normalized to the maximum of the power here, P max. So this is the first quantity that we define. So what does this represent? This is nothing but a normalized power pattern of the antenna, which is integrated over full sphere for 4 pi. So the omega A so obtained in this case is the solid angle of an idealized antenna, right? Whose power pattern Pn is equal to 1 inside omega A and it will be 0 outside. Of course, such an antenna does not exist, but it's a measure of this quantity, right? So correspondingly, what we can also define omega main beam. In this case, this is the main beam. So integral instead of 4 pi is actually standing over main beam. And then we come to a quantity called the main beam efficiency, which is the ratio of omega main beam and omega A. So the main beam efficiency is actually telling me how the power is concentrated in the main lobe. That's what it's telling me. But one should not be confusing this with the fact that a high main beam efficiency would imply a low main beam efficiency would in any way be related to the angular size of the main beam. You can have a very small antenna which will have a very large main lobe, for example, and in that case, but if the most of the power is concentrated in this main beam, then it would have a very good efficiency still, but does not necessarily mean that it has a very good capability to give you the resolution also, no, right? So directivity depends on how well the power is concentrated in the main beam. That's the first quantity that we describe. So next, when we point our antenna to the sky, what is it that we observe? So monochromatic power that is received by an antenna is represented by this. P nu is telling that I'm receiving power in a very small bandwidth, and A effective is the effective area of the antenna. It's different from the geometric area of it, and S nu is the density of the source that I am observing in this case. So what we get here, antenna, if this is the power distribution, power pattern of that antenna, and P nu, in this case, half effective, and this is the normalized power pattern, and this is the brightness distribution of the source, B nu theta phi, right? So this is what we will get. And if I get brightness, I use Rayleigh-Jeans approximation, I can write brightness like this, 2k by lambda square TB. So this TB is, we call it brightness temperature, but it's only a convenient quantity to represent the brightness of the source. It has nothing to do with the thermodynamic temperature in general, actually. Of course, if we are observing a black body, then these two will get related, but otherwise it is not. And I'm sure in this summer school, you have come across many such temperatures, like spin temperature, excitation temperature. And so this is one more such quantity which does not have anything to do with the thermodynamic temperature, right? And if you plug this back into this, you can define antenna temperature like this. This is TB, which is defined here, and then this is the power pattern, and then this is the solid angle over which we are integrating. And if we go back, you can see that like I can replace omega A here with this integral Pn theta phi d omega. So antenna temperature turns out nothing but the convolution of the brightness temperature with the beam pattern. So what is the antenna temperature in this case? It is the beam average value of the brightness temperature of the source. This, of course, intuitively also it's making sense. And since if you're not familiar with convolution, just keep this idea in your mind. Tomorrow, in my next lecture, I'm going to cover some basic concepts of Fourier transforms also. So then it would become clear to you that what this expression is corresponding to. Right. So next, now trying to understand that how you can connect with the sensitivity of a detector. We have already made the connection between antenna and the sky right here. So this connection has already been made through this equation. Now we try to understand that how we can understand the sensitivity of this detector. So for this, let us consider this following thought experiment here in this case. For this, what we are going to do, look at this cartoon here. What we have shown here, so this one is, we are talking about an antenna which is enclosed by a black body at temperature T1 here. And its output terminals are actually connected to a transmission line in this case, right? And which is also terminated by a matched load, which is a resistor here R. And by matched means that there are no losses, and this resistor is having the same impedance as the transmission line. So if the transmission line and the resistor are decoupled from the outside world, that is, we isolate them, then from the second law of thermodynamics, we know that they would reach a thermodynamic equilibrium, which will be identical to the black body temperature. And furthermore, the two powers, P1 and P2, if they are flowing between them, I could show an arrow here and another arrow in the reverse direction here. Those will also become identical. What is this? This is nothing but the famous Nyquist law, which says that power is actually related to kT. Here. We say that a resistor at the temperature T produces a noise power kT, and since it is integrated over bandwidth, then I can also multiply bandwidth here, delta nu in this case. The origin of this power is what it is actually thermal motion of electrons within the system, due to which, even though the mean current that you would detect, if you measure it, it will be zero, but the RMS will not be. And due to which the resistor which is here, it will provide a non-zero power input to the amplifier. And this is a very famous idea. It goes by the name of Johnson noise. Right? You can also look at it in more detail, but this is the power output that we are talking about. So now going back to the two things that we have determined, this is a power and this is the received power of vector S nu delta nu. And I can relate these two, then I come across this expression which relates flux density of source to the antenna temperature, which, as you would recall, we have already derived in a more general fashion as well. So this quantity gamma here, which is just the reciprocal of this, is Ta by S nu. This is called gain. This represents the sensitivity of the antenna in Kelvin per Jansky, right? And it directly corresponds to the collecting area, which like the total amount of photons that they are collecting, the detector is collecting, and it represents the amplitude of the antenna temperature for a given source. So this is what we mean by sensitivity of the telescope. And this quantity for a telescope or a detector can be measured by observing a calibrator, which is nothing but a source of a known property. Sometimes it can be an astronomical source, but we can also use artificial sources for this purpose as well. Right. So here I am again not going into great detail of each of the systems shown here, but because that's something we will do in the next lecture. But here I want to show you what is it that a radiometer or a setup through which we detect radio signals consists of. So here we have an antenna. Since the signal is very weak, immediately we need to put an amplifier here before we do any electronic operation on that. And then often there is a mixer which is used to shift the signal to a different frequency. Often it is a lower frequency where which electronics can operate better, or it's more efficient to transfer the signal. Then there can be another amplification stage, and then there can be detector. And of course, prior to that, I can digitize the signal also and do various other things as well. But these are the very basic entities that we have. So the total system temperature till up to this point, we have only been talking about what is the antenna temperature, but the total temperature that my system has actually would be a contribution of noise from each one of these setups. So if TR represents the temperature from the entire receiver chain, then Tsys will be TA plus TR here, right? So if I'm detecting a certain signal, it will also have a noise or fluctuations on top of it, which is delta T, and this will correspond to Tsys and divide by square root of delta mu tau. This is what this is corresponding to here is that the precision with which I can make the measurement of the temperature uh, is delta T, and the denominator I have delta nu, which is the bandwidth, and tau, which is the integration time. So the bandwidth is describing the total number of events per unit time, and since it is multiplied by time, then this is the total number of events or the duration of measurement over the duration of measurement I have. So this is telling me that the accuracy which I have in my measurement. So the signal to noise ratio, which I can define as TA by delta T, because I'm interested in TA, I'm not interested in these quantities, will be this. And this should be, of course, made as large as possible, at least greater than 3 if we are talking about Gaussian statistics. And to make this, we need to have larger effective area, but we can also increase the bandwidth over which I am measuring the signal, and I can also increase the duration over which I am making the measurement. And of course, lower the Tsys, the higher will be the signal to noise. And I'm not going into the detail of this, but you can find out from any signal processing book that first stage of the amplification is most important, because this is where most of the noise is getting added to the signal. So what we have done here is that we have talked about put this as low noise amplifier, and these amplifiers are also actually cooled so that like the thermal noise can be reduced as much as possible. So another figure of merit that we can define for antenna performance is system equivalent flux density. It is very closely related to this. If you look at this expression here, 2K effective TA. So we have 2K Tsys A effective. This goes by the name of system equivalent flux density. And eta prime is the system efficiency, and for nice systems, it is usually close to 1. So signal to noise in terms of this will be S nu square root of delta nu by SEFT. So any telescope design that we will have must minimize system temperature or Tsys. And this may actually require either making telescopes which are big, or it may also require cooling some of the components in the receiver chain so that the noise contribution by them is very, very small. So I'm going to stop here for today, because today I wanted to introduce to you that what kind of unique contribution that radio astronomy has made to our understanding of celestial objects and universe. Then, of course, as I highlighted that, let's remember and refresh our concepts that radio waves interfere like any other electromagnetic wave, and also the signals are weak. And now we have understood that the kind of things that we need to do to actually detect these weak signals, which is actually to have telescopes which will minimize this, so that I have low Tsys and I can have large bandwidth, and also eventually if I need, I can also integrate for long over during my observations. And then we saw that although the initial takeoff of radio astronomy was not smooth, but now it's a very well developed field. And in next two lectures, we will see that some of the very new telescopes that are coming up online and how they will, I will also discuss some of the science cases that they will address. And talking about antennas itself, we try to understand some of the basic quantities through which we can define their performance, namely directivity and gain. And we have also looked at the importance of the system temperature, why it is so important to keep it low. So my next lecture with you will be on Wednesday, and in that we will look at different types of telescopes. I will discuss some of the basic properties of Fourier transforms, and also eventually like the interferometry, which is really very interesting concept, very technically as well. So this is the end of today's lecture, and now we can have some questions actually. So first I can look at the chat window. Is that okay?
Yes, sir, go ahead.
So where is the chat window actually? I can stop sharing, maybe that would make it easier. Yes, now I can see. So right. Okay, so chat is enabled. As you can see, I will not be able to take all the questions, so I'm just. So first question is that aren't radio waves actually getting scattered and getting modified? Yes, of course they are getting modified, and that's why we will do calibration. And I'm going to talk about that in my next lecture. That what are the effects that we need to take care of before we can actually understand what information is there in these radio waves. Okay, 21 centimeter line. Okay, I went through this 21 centimeter line very quickly because I thought that is something that has already been covered. How do we choose it? Okay, I will talk. How do we choose a particular frequency in radio frequency range? This is something we are going to understand in more detail, like how we can tune our radio telescope to observe a certain frequency, especially if we are observing certain spectral line, then we will need to actually tune our telescope such that we are able to pick that radiation. So what is the effective area of an antenna? So geometrical area of an antenna may be something, but that's not what is relevant here, because I will talk about in my next lecture that the collecting area, or the area over which the photons are actually reflected or received, depends on the portion of the antenna that has actually been illuminated. So this is something I will cover in my next lecture, that how it is different from the geometric area. That's a good question. Somebody has asked, can we apply some sort of noise filters in the detector stage? Since we're interested in small bandwidths of frequency. Yes, of course, especially like when we have radio frequency interference, for example, coming from satellites, which is confined to certain frequencies, we do apply filters which are actually used to reject those noisy frequencies. So this is pretty much the. So now shall we go to the Google Doc? Actually, we can look at that now.
Yes.
How to find digits. Okay, selected questions, and there are all questions. Okay. Okay, the first question is asking about what is quasars actually. So I suppose there have been a detailed lecture on AGNs. So what we are referring to quasars actually by name, if you just try to deconstruct the name, it is referring to a quasi-stellar objects, which is something which looks like a star, but of course it is not a star. Quasars are very luminous objects. And they are so luminous because they are actually emitting radiation through a totally different process. And what happens that at the center of this process is a supermassive black hole, right? And most of the large galaxies have such black holes, and their masses ranging from millions to billions of times the mass of our sun. In quasars and also in other types of AGNs, what happens that this black hole is surrounded by a gaseous accretion disk, very small disk. And what happens that as gas from this disk actually falls to the black hole, the gravitational energy from this is converted into energy, and this energy is then released in the form of electromagnetic radiation, right? And this radiation that comes out of this process, it's huge actually. It is actually have luminosities thousands of times greater than, like for example, our galaxy. So that's in very brief, in very simple terms, what quasars are and why they are so much luminous. So they are not illuminating by phenomena like fusion in stars or in sun, right? This is a very totally different physical process that is involved here. That's why they are so luminous, and they're so luminous that the energy from the quasars can actually outshine the entire galaxy completely. So next question is that what all techniques are used for cooling of the electronic components? So so people use different kinds of coolants. For example, liquid nitrogen can be used, and a receiver can be submerged in that. That will keep its temperature much lower than the ambient temperature. That is one very standard technique to cool electronic components. But this is an expensive technique. So a telescope, if certain component we want to cool, we need to actually design or plan it well in advance. It is not something which can be done just like that. So, and you would also find that not many telescopes actually use this technique of cooling the receivers because it is very expensive to incorporate as well. But it is a commonly known technique to reduce the thermal noise introduced by the components. So this is so to the organizers and moderators. What's next? Can we stop now, or am I supposed to unmute some of the members for some questions?
I
Hi
don't.
Neeraj,
There
Santosh
are.
here.
Hi, Santosh.
Hi, I guess we can stop because right now we don't have the
Hand raised.
anybody has raised the hand,
Okay.
and maybe you have completed your all questions from your chat.
Very much actually. The only thing which I have not answered is the 21 centimeter line, because that was a very general question. But very briefly, I can say is that it is at 21 centimeter because that's the energy separation between the two hyperfine states of the ground state in which it is split. But I can cover a little bit more of it in my next lecture.
Okay, fine.
Okay, I can probably present some diagram for that. That would make it easier to understand. Okay, I can show energy levels, and I can explain what is fine, hyperfine from there.